Number 1. Yersinia pestis and the living reservoir. You are a public health officer in Western Kazakhstan in the summer of 2013, and the man in front of you has a swelling in his groin the size of a fist. You know what it is. He is dead within 72 hours. The bacterium that produced that swelling killed roughly 1/3 of Europe between 1347 and 1353. It never left. Yersinia pestis lives in rodent reservoirs across Central Asia, the western United States, and Madagascar. The WHO records between 1,000 and 3,000 confirmed human cases every year. The 2013 Kazakhstan outbreak was confirmed and contained. U.S. prairie dog colonies in Arizona, New Mexico, and Colorado test positive for Yersinia pestis on a routine basis. In 2014, a strain isolated in Madagascar showed resistance to multiple frontline antibiotics. The bacterium that killed 1 in 3 Europeans is not a historical artifact. It is alive, it is in the soil, and it is in animals within driving distance of American cities. Antibiotics treat plague effectively if administered early. Modern surveillance systems detect outbreaks faster than any infrastructure available in 1347. The public health architecture of the developed world is incomparably better equipped than medieval Europe. But the Madagascar 2014 strain showed resistance to the antibiotics that architecture relies on. The incubation period of pneumonic plague is 1 to 3 days, faster than most outbreak detection systems can generate a confirmed result. The conditions that drove the 1347 pandemic, malnutrition, rat density, port cities without sanitation, exist today across parts of sub-Saharan Africa and South Asia. Climate models show rodent reservoir ranges expanding northward as temperatures rise. Every major plague outbreak in history began with a single index case nobody recognized in time. The bacterium has not changed. The question is whether detection moves faster than incubation. Yersinia pestis is the most studied pathogen on this list. The next is the least studied because for 600 years scientists assumed it was gone. Number 3. Plague's pneumonic form and airborne transmission. The WHO classifies pneumonic plague as a potential bioterrorism agent at the highest priority level, Category A, alongside smallpox and anthrax. And that classification is based on a single transmission property that medieval Europeans discovered the hard way. That property is this: pneumonic plague does not need rats. It transmits person to person through respiratory droplets. No flea, no rodent, no contaminated water, just breath. Paul-Louis Simon confirmed flea transmission of bubonic plague in 1898. That finding made plague manageable. Remove the vector, stop the spread. The pneumonic form bypasses the vector entirely. Its case fatality rate without treatment approaches 100%. In 1994, an outbreak of pneumonic plague in Surat, India, caused 500,000 people to flee the city within 48 hours. They were already potentially infectious when they left. In 1347, it took the plague months to travel from Crimea to Sicily. A flight from London to Sydney takes 24 hours. The version of plague that killed fastest in the medieval period was not the bubonic form, it was the pneumonic form, and pneumonic plague does not need rats. Pneumonic plague is treatable with antibiotics if identified within 24 hours of symptom onset. Modern diagnostic systems are fast. Airport health screening catches symptomatic travelers before they board, but the 24-hour treatment window assumes immediate correct diagnosis. Pneumonic plague presents initially as influenza. Airport screening catches symptomatic travelers. Pneumonic plague is contagious before symptoms appear. The 1994 Surat outbreak showed that even a contained pneumonic cluster causes the population movement that accelerates spread. The antibiotic-resistant Madagascar strain is pneumonic capable. Plague kills fast. The next pathogen on this list kills slowly, which is why it has been harder to eradicate. Number 4. Leprosy and the armadillo vector. In 2011, a microbiologist named Richard Truman published a paper confirming that leprosy was jumping from armadillos to humans in the southern United States. The strain responsible was genetically identical to the medieval European strain. Leprosy, caused by Mycobacterium leprae, was considered eradicated in the United States by the 1960s. Medieval Europe had an estimated 1 million lepers at the epidemic's peak. The 9-banded armadillo is the only wild animal reservoir for M. leprae in the Americas. Armadillo range is expanding northward. The animals are now established in Tennessee and North Carolina. A 2015 CDC report confirmed that 35% of U.S. leprosy cases were linked to armadillo contact. Florida reported a record number of new cases in 2023. Local transmission with no identified armadillo contact was documented in several of those cases. The pathogen that built 1,000 leper colonies across medieval Europe is expanding its American range inside an animal whose territory is moving north with the climate. Leprosy is curable with multi-drug therapy. Transmission requires prolonged close contact. Casual exposure does not produce infection. Modern cases are mild compared to medieval presentations, but multi-drug therapy takes 6 to 12 months and requires consistent access to medication. Mycobacterium leprae has the longest incubation period of any known bacterial infection, up to 20 years. Armadillo contact in the American South is common and largely unmonitored. The 20-year incubation means exposure happening today will not produce visible cases until the 2040s. Medieval Europe's leprosy epidemic built slowly over generations before institutions recognized its scale. The same incubation dynamic is in operation now. What is happening in armadillo populations across the American South right now will not show up in human case counts for 2 decades. Leprosy's threat is slow and invisible. The next pathogen moved fast the first time, and it has never been definitively identified. Number 5. Sweating sickness and the hantavirus connection. In 1551, a physician named John Caius documented an outbreak in Shrewsbury that killed healthy adults within hours of the first symptom. The disease he described has never been definitively identified. Caius recorded the full symptom profile: sudden onset, profuse sweating, cardiac collapse, death within 3 to 18 hours. It preferred healthy adults over the elderly and children, the opposite of plague. Sweating sickness struck England 5 times between 1485 and 1551. Then it stopped. No confirmed case has ever occurred since. In 1997, Guy Thwaites at Oxford proposed that sweating sickness was a hantavirus. The symptom profile matches hantavirus pulmonary syndrome precisely: rapid respiratory failure, cardiac involvement, highest mortality in young, healthy adults. Hantavirus reservoir is rodents. Sin nombre hantavirus in the U.S. Southwest produces identical rapid respiratory failure in its victims. Hantavirus does not disappear between outbreaks. It retreats into its rodent reservoir and waits. A disease that killed Henry VIII's closest companions in hours has no confirmed cause, no confirmed extinction, and a symptom profile that matches a pathogen family currently circulating in rodent populations across 2 continents. The hantavirus identification is not confirmed. Other hypotheses include anthrax and a novel influenza strain. Sweating sickness was largely restricted to England, which suggests a localized vector or environmental condition rather than a broadly circulating pathogen. But hantavirus does not disappear, it retreats into rodents. A strain that emerged from rodent contact in 1485 could re-emerge from the same reservoir if the same contact conditions recur. The 1485 outbreak followed a period of urban rat population expansion in English port cities. No other proposed pathogen fully accounts for the symptom profile Caius documented. Sweating sickness remains unidentified. If Thwaites is correct, the reservoir is still alive. If the pathogen emerged once from rodent contact, it can emerge again through the same route. Sweating sickness may be hiding in a reservoir. The next pathogen is not hiding. It has been in European grain fields for 1,000 years. Number 6. Ergotism and the returning fungal threat. You are a doctor in the French village of Pont-Saint-Esprit in August of 1951. Your patients are describing the sensation of burning in their limbs. Some are hallucinating. 3 have developed gangrene spreading from the extremities inward. It is the symptom cluster that medieval chroniclers called St. Anthony's fire, and it is being produced by contaminated bread from the village bakery in post-war France. Ergotism is caused by Claviceps purpurea, a fungus that infects rye and other grains. Medieval outbreaks are documented from 857 AD onward. The Annales Xantenses describes a mass killing in the Rhine Valley that year. The 1951 Pont-Saint-Esprit outbreak killed 7 people, hospitalized 50, and caused mass hallucinations. It passed through multiple grain inspection checkpoints before reaching consumers. In 2019, a study found ergo-alkaloid levels in European grain supplies rising year on year. The Claviceps range is expanding northward with warmer growing seasons. Contamination events in grain crops are increasing in frequency across northern Europe. Ergotism killed tens of thousands in medieval Europe, occurred in a French village with functioning food safety systems in 1951, and the fungus that causes it is currently expanding its range in response to warmer growing seasons. Modern grain inspection systems catch ergot contamination. Treatment is available for acute ergotism if identified quickly. The 1951 outbreak was an anomaly in an era of improving food safety. But the 1951 Ponce Esprit grain passed through standard inspection before it reached the bakery. Ergot alkaloids are not always visually detectable in flour once milled. Climate expansion of the claviceps range means contamination events will increase before inspection protocols can adapt to new geographic patterns. Low-level chronic ergot exposure produces neurological symptoms that are routinely misdiagnosed as other conditions. The fungus never left. It retreated when rye consumption declined and grain inspection improved. Rye consumption is rising in health food markets across Europe and North America. Claviceps range is expanding into grain-growing regions where monitoring protocols were designed for temperate conditions that no longer apply. Ergotism returns when the food supply changes. The next pathogen on this list returns when the ground thaws. Number 7. Anthrax and the thawing animal graves. In the summer of 2016, a 12-year-old boy died of anthrax in the Yamal Peninsula of Siberia. The source was a reindeer carcass that had been frozen in permafrost for 75 years. The spores inside it were still viable. Anthrax killed medieval livestock across Europe and Central Asia in repeated outbreaks. Dead animals were buried in mass graves called plague fields in the Russian and Central Asian historical record, often without lime treatment that would have neutralized the spores. Bacillus anthracis spores are effectively immortal in frozen or dry conditions. There is no known upper limit to their viability period. Boris Revich at the Russian Academy of Sciences has identified over 30 anthrax burial sites in Siberia at risk from permafrost thaw. The 2016 outbreak hospitalized 96 people and killed 2,300 reindeer. Summer 2020 saw Siberian temperatures 18 degrees Celsius above the seasonal average. The medieval animal graveyards are still there. The spores in them are still viable, and the permafrost that has kept them frozen for 7 centuries is thawing. Anthrax has an effective vaccine. Antibiotic treatment works if administered early. The 2016 outbreak was contained relatively quickly with modern emergency response, but the 2016 outbreak occurred in a region with no standing anthrax vaccination program. There had been no anthrax there in living memory. Revich's inventory covers only part of Siberia. Central Asian and Mongolian plague fields have not been systematically mapped. Human anthrax from spore inhalation has a case fatality rate exceeding 80% without treatment. Thaw zones are precisely the regions with the least medical infrastructure. The 2016 outbreak was the first confirmation that medieval animal plague graves can release viable pathogens. It will not be the last. The question is whether the next release occurs near a population center with detection capacity or in a region that has not seen anthrax in so long that nobody is looking for it. Anthrax returns from the ground. The next pathogen on this list never left the water. Number 8. Typhoid and the drug-resistant urban strain. There are more people alive today without access to safe drinking water than there were people alive in total during the entire medieval period. Typhoid killed more medieval urban dwellers than plague in most years. It was not epidemic, it was endemic, a continuous low-level mortality that cities accepted as a fact of life. Salmonella typhi, the bacterium that causes it, was never eradicated. The WHO records 11 to 21 million new cases of typhoid annually. It is among the most common infectious diseases on Earth. The extensively drug-resistant typhoid strain designated XDR emerged in Pakistan in 2016. By 2019, it had spread to 30 countries. It resists ampicillin, chloramphenicol, trimethoprim, sulfamethoxazole, and fluoroquinolone simultaneously. The Flint, Michigan water crisis, which ran from 2014 to 2019, demonstrated that water infrastructure failure in a wealthy, developed American city is not a historical anomaly. It is a systems failure that can occur wherever infrastructure investment is deprioritized. Typhoid never came close to eradication. It is among the most common infectious diseases globally, and the strain currently spreading across 30 countries resists every first-line antibiotic. Typhoid vaccine is effective and widely available. Water treatment in developed countries reliably prevents Salmonella typhi transmission. Last resort antibiotics can treat XDR typhoid in most cases, but last resort antibiotics for XDR typhoid are expensive and not universally available. Resistance to those last resort drugs has already been reported in isolated cases. Climate flooding events contaminate water supplies in developed countries, documented repeatedly across Bangladesh, Pakistan, and the U.S. Gulf Coast. The conditions that sustained medieval urban typhoid require nothing more than water and sewage sharing the same infrastructure. That is the current reality for roughly 2 billion people. The XDR strain is the first since the pre-antibiotic era to threaten treatment failure across multiple drug classes simultaneously. What medievals called a fact of city life, the WHO now calls an emerging crisis. Typhoid lives in the water supply. The next pathogen lives in the air, and it has already shown what fast looks like. Number 9. Tuberculosis and the drug-resistant return. The WHO declared tuberculosis a global health emergency in 1993, the first time in its history it had used that designation for a disease that already had an effective treatment, and the reason it gave was a pattern that medieval physicians would have recognized immediately. The pattern was this: the treatment was failing. Drug resistance was producing TB cases that no available antibiotic could reliably clear. For the first time since the medieval period, tuberculosis was becoming an untreatable death sentence in affected populations. Mycobacterium tuberculosis has killed more humans than any other pathogen in recorded history. Otzi the Iceman, who died 5,300 years ago, carried it. Medieval European urban populations had estimated latent infection rates of 40 to 60%. The WHO reports 10 million new TB cases annually. Extensively drug-resistant TB, XDR-TB, is now present in 127 countries. In 2021, TB killed more people than COVID-19 in low-income countries. There are strains of tuberculosis circulating right now that no antibiotic on Earth can reliably treat, and those strains are in 127 countries. XDR-TB is still a small fraction of total TB cases. Treatment success rates for drug-sensitive TB are high. New drug regimens are in development and showing genuine clinical promise. But the XDR-TB fraction is growing, not shrinking. WHO data shows consistent year-on-year increase. New regimens require 6 to 18 months of consistent treatment. The populations most affected are precisely the populations with least consistent treatment access. Multi-drug-resistant TB, the step below XDR, is now endemic in parts of Eastern Europe and Central Asia. The trajectory of resistance acquisition in tuberculosis is ahead of any other bacterial pathogen currently monitored. The two competing truths are these: TB is curable, and TB is becoming incurable, and both are true simultaneously. Which one applies to you depends on which strain infects you and where you are when it does. Medieval TB killed because there was no treatment. XDR-TB kills for the same reason. The mechanism is different and the outcome is identical. Tuberculosis is the slow return. The last pathogen on this list is the fast one.